Hello, welcome back to the today class. Today we will talk about viewing transformation. So these are the today class objectives. You need to know the camera setup parameters, also which that you can understand the viewing and projection process, which are related to the chapter 4 of my book. Also last time we briefly went over some components of the rendering pipeline. And then we see that actually a lot of components of the rendering pipeline related to the 3D transformations. That's why we talk about these techniques. And then also the last time we talked about 3D rotation in the context of utilizing the concept of the frame. And then also talk about the geometric meanings of the dot product, also the cross product. We will see that we will utilize these operators a lot for deriving some other operations and concepts in the computer graphics. Also, I went over your questions. I found this question. One of you mentioned that last time we talked about rendering pipeline, right? It seems to him or her that trivial rejection, the modeling transformations, also they're very similar to this clipping. I think that these are quite valid observations. Actually, there are certain difference between the trivial rejection clipping. So the trivial rejection is like this. Suppose that you are looking at the object something like this. This is actually your camera view volume here. Actually, this is your image plane located here. And then maybe the sum of the object, maybe they're even located behind the image plane, right? Then you can reject. You don't even need to render this object, right? So in that sense, I mentioned that that's the trivial rejection. But the clipping is that here some of the triangle maybe they're span across this view volume, right? Then you need to clip. You need to actually clip away the invisible portion, right? So it's a little bit it is a little bit different, but actually but nonetheless. We can apply the similar operation in one component of the rendering pipeline, also another component of rendering pipeline. So actually, there could be the many different options that we can realize, or we can implement some of this concept. But actually, in the end, we need to optimize the rendering performance, right? We need to show the very fast performance for the game and some other applications, right? So we need to think about it in what places is the best places for performing some of these operations. I think that in the end, this boils down to the optimization of this rendering performance. Actually, we will talk about some of these issues later on. Okay, so these are actually the scheme of the rendering pipeline. And today we will talk about this viewing transformation. Viewing transformation is that we set up the camera in the world, and then we know that this actual camera, we know that this coordinate of this model in the world coordinate, right? We also set up this camera in the world coordinate. But for for rendering this model, in the end, we need to transform of the coordinate of this object defined in the world coordinate into the camera space, right? In other words, so suppose that you actually you have certain point in the 3D space like in the world space like this, right? But for rasterization, for render is nothing but you need to actually compute the coordinate of this point in the image space, right? So basically they're setting up this camera and computing this camera coordinate the coordinate in the screen space of this object is actually nothing but viewing transformation. That's what we wanted to do today. And then you can see that this actually composed of rotation and translation. I will talk about this later on. Again, so first of all, we need to set up the camera, right? First of all, we need to specify the position of the camera, also orientation of this camera, right? So I can use my 3 fingers to define the kind of the frame of this camera, right? I can rotate it like this, also I can move around this position of the camera. And this actually defines a frame for our eye space, or sometimes I can say that it's screen space or image space. So these are actually the common camera coordinate. So also this visualizing this the frame of the camera. So camera, we actually define in this camera at the camera origin, and then usually this is the y vector of this camera space, and this x vector, and then we usually put this g axis aligned with the view direction, but actually this g direction increase that direction actually. That's not the other way. So basically the g direction heading that that direction. So these are actually the common setup of this camera, and also basically we actually set up this camera parameter at the world space. And once we set up this camera in the world space here, then as I mentioned before, we need to compute the coordinate of this object in our image space, right? That's also the viewing transformation. And then to do that, we can see that actually we can basically this camera is located in the world space, right? Somehow we translate or rotate it in a way that we can actually align into this canonical space like this, such that actually this origin located at the center of our screen. So in the end, basically we need to compute the coordinate of this world in image space, right? This is nothing but this is one illustration of our image space, but in 2D. But actually, this is actually our the screen space, right? We need to compute the color of every the pixel, right? And then to do that, we need to compute the coordinate of this object here, right? To do that, actually, you may remember that we used this kind of canonical coordinate. You know, the center is located there, and then this might be -1 and 1, something like that, right? So ideally, we need to transform this coordinate system of camera in a way that we can align that into like this. So the g direction should be located heading for that direction actually. That's the viewing transformation. I will talk about that one. First of all, let's talk about how we can actually specify this camera. So these are some of the very kind of intuitive way of specifying the camera. Typically, here the eye point. Basically, this is actually origin of the camera. Here, I say that E dot, and then we can also define this viewing direction, right? So here I'm looking at that direction, right? I can define viewing direction, but instead of using the viewing direction, we can also use the look at point, center of images. So for example, I'm here. This is my camera origin. I want to look at here. Basically, in other words, I want to make sure that this point in the center of my screen space here. So you can actually compute given that for some of you, for all of you, it's very intuitive to define the vector direction, right? But some people they may not know. Basically, they may not fully understand the concept of the vector, right? So that so that's why actually they prefer to use the look at point, which is actually more intuitive, and more people can understand this concept instead of defining this direction. So that's why actually we prefer to use this look at point, which is more human friendly to also more widely accessible to more people. And then you define this lookup vector here, lookup vector. Basically, I can look at you that way, but also I can rotate like this, right? At that case, my lookup vector that direction. So basically, this is the lookup vector is actually head toward the upward of my image actually. So in this case, my lookup vector may be heading that one. These are actually some of the intuitive quantity. Based on that, basically we need to define. We can also define the affine frame, right? The 4x4 matrix. So starting from this intuitive parameter, we can first define this look at vector, look at direction, right? So here, look at direction is basically our camera origin located here, and then we are looking there, right? And then basically by taking out the E from the point P, we can define the vector, right? That's actually look at vector. I define this L, P minus E is a point, and then I use this L head, which is actually normalized vector. Basically, I divide this L vector with each magnitude. So now it defined actually this look at vector looking direction. Also I compute actually also I compute this right vector here. Right vector is basically I define here basically this is my look at vector. This is my look at vector, and this is my right vector, something like that. So heading at that direction. So to do that, how I can do that? The right vector should be the orthogonal to should be orthogonal to my up vector, also this viewing direction, right? But I already know my look at vector, right? L vector. Also I know the look up up vector, right? And then I do to define. You might remember that to define the vector that are orthogonal to both of them, we can use this cross product, right? And then if I wrap up these two vector with my right hand, you can see that actually I can get that direction, the right vector, the vector heading toward my right side, right? So that's why actually I got this right vector, known as the R vector. Also, I can compute this right vector by dividing the R vector with each magnitude. Okay, so basically now we computed this look at direction, also right vector, something like that, right? And then also you might remember we already specified the up vector, right? But this up vector may not be the perpendicular to these two vector, right? I mean we let the user to define the up vector, right? But obviously it's very depending on the people, actually they can define the up vector something like this. So here this viewing direction, and then some people may define the up vector something like this, right? This is not orthogonal to there, right? So we let the user can specify kind of the general direction of the up vector, but we actually adjust it in a way that the modified up vector should be orthogonal to this look at vector, also the right vector that we defined here. To do that, we adjust the up vector again, and then to do that, we also performing this cross product between the R vector and L vector. And by wrapping around the R vector and L vector, then we actually wrapping around the R vector and this vector, that way we can actually get this up vector that direction. Since these two vectors already the unit vector, this adjust up vector already the unit vector. Okay, so now actually we specify this direction of we already know this kind of a fine frame of this camera, right? We know this the look at vector of vector, so right vector that direction, right? And then we can define a fine frame of there, right? And then now next step is that we somehow translate rotate in a way that this actually mapping to that direction. The G direction should be heading that direction, not the other way. This is actually our approach of the aligning process. We have first of all we translate the camera origin to the world origin, right? And followed by sorry, not the world origin. Actually, we align we translate camera origin of kind of the world origin, which is actually turn out to the 0, 0 and 0, 0, and then we follow by rotating the camera so that actually the center of that way we can actually make sure that all the points are located in this canonical space. So in other words, suppose that you define the coordinate in the world space like this, right? And then you actually you basically translate the camera origin. Basically, you take out the camera origin, right? That origin should be located at the 0 and 0, 0 in the world space, right? And then we rotate it. Actually, we rotate camera origin to this canonical direction into this canonical direction. In this case, x is the 1, 0, 0 the direction, right, and so on. Then at that case, actually, we can say that that's in at that case is after taking this transformation rotation, we know that actually that coordinate located in this I space, so that I actually use the E. Is the I coordinate actually. So that's what we are doing. That we can do. That's actually our approach to transform this coordinate from the world to the actual I space. So the question is that how do we compute the rotation and translation? Let's first talk about the rotation component. I already mentioned it here, right? So basically, the E is I already defined, right? The E vector. The frame or fine frame of the E I space is defined by something like this, right? This actually the x coordinate. Basically, x is actually here. We define the R vector located heading that direction. So that's why we print the R vector here. Up vector here actually is the y direction there, that direction. And G, the lookup vector, we define the lookup vector. Something like that direction, right? But we wanted to make sure that we'd like to set up the G direction heading that direction, right? So we need to reverse it. So that's why we take this minus L. So that actually with the L vector, the minus L vector located minus L should be the G direction. This canonical the G here. Here we didn't worry about the translation here, and then we do basically we somehow do the rotation within this affine frame. Then we wanted to make sure then it will be under this canonical space of the world here, something like this, right? This is actually identity matrix. So in this context, then we can see that ideally we need to compute this rotation matrix, right? But to compute this rotation matrix, we need to take the inverse of this matrix, right? But fortunately, this vector is also normal. In other words, these three vectors are actually orthogonal to each other, and they have a unit vector. In that case, one can show that the inverse of this matrix can be computed by the transpose, right? And then by taking this inverse of here to there, then RB can be computed by the transpose of this matrix. In this case, R transpose, U transpose, and the R vector, RU and L vectors actually transpose. Okay, so now actually we computed this rotation part. Now the translation is very easy, right? The translation located here, basically we cancel out the camera origin. To do that, actually, there will be within the 4x4 matrix. This actually the 4x4 translation matrix. We got just taking the minus of this camera origin, minus EX, minus EY, minus EG, with the identity part here, this rotation part, and then 0, 0, 0, 1. And then basically this actually nothing but same equation here, right? I already mentioned that if we do that, actually this equation, basically these two parts actually they're equal to each other, right? So we already computed this part, and then if we rewrite it, we don't need to worry about this camera coordinate. Then basically they are equal to each other, right? So given that we cancel out the camera, we set the camera origin to the origin and rotate it, then at that space, the coordinate is defined in the I space, right? That's actually the viewing transformation. Basically, viewing transformation is nothing but somehow align transform the coordinate defined in the world space into this camera space, this I space. So as a result, the V is actually this part, this actually viewing transformation, and then we already defined the RV and this transpose. Then we can actually have this one, and then if you do this kind of the matrix or multiplication, you can get this kind of the shape. So now let's talk about how we can actually how can we set up this camera in this OpenGL. So basically the OpenGL provider this API. Basically GLU look at. So GLU look at, if you call this function, it actually under the hood of this API, it actually defines this transformation. and then when you do the rendering, it applies this concept this matrix. Also, the GLU lookup also require you define the I point, center the lookup point, also the up vector. Actually, it's actually the same thing that we talked about in before. Also, there are some of the if you look at the some of the recent OpenGL require you to directly work with the matrix. Then also some of the recent matrix, some of the recent OpenGL, you can use this kind of library, and also it provides very similar API, the lookup. So basically, if you know, my main message is that once you know this concept, you can actually identify this corresponding API. Since the concept can be changed very, it takes much more time for changing the concept, but actually this API, the low-level API, they keep changing based on this long-lasting this concept. Okay, so if you look at the skeleton code of PA2, here now we actually you can see that this GLU lookup, right? And then basically GLU lookup nothing but actually setting up your camera. I will talk about some other components later on once we know that some of their concepts. Okay, so now we define this coordinate of the world, coordinate of this object in the world space to the one in the image space, right? We did that, right? But you can see that ideally our image space is 2D, it's not on the 3D, right? So we need to do this projection. Projection is nothing but map the 3D point into the map. Basically, if we do this kind of operation, still actually we got this 3D point, right? So now we have flattened this point into the 2D. So map the 3D point in the I space into 2D point in this projection, this image space actually. There are two common methods. One is orthographic projection, also this perspective projection. First of all, this orthographic projection, you might see this kind of image before, right? So it's nothing but project the point along the parallel line to this parallel line. So basically, also because of that process, is also known as this parallel projection. It typically used for the top and side view in the drafting, also the modeling application. Sometimes actually we want to actually look at look at the object in orthographic projection. If you use the common 3D modeling tool, it also provides this kind of orthographic projection. You can see that in this image is drawn by the orthographic projection. You can see the actual parallel lines actually maintained even under this orthographic projection. The question is how can you implement this one? It's very simple, right? Suppose that we transform all the world coordinate into this I space, right? And then just flattening, right? So basically the 3D point may have this X, Y, Z component, right? But ideally we want to, the orthographic projection is nothing but we maintain X, Y component, but we actually flatten G, right? In other words, we maintain X, Y. This actually after the X prime, Y prime, G prime is the coordinate after this orthographic projection. We maintain it. We actually X prime is nothing but X, Y prime is Y. But G component is nothing but we set the 0, 0, 0, 0 here. So in other words, we cancel everything. Now after the orthographic projection has the 0 component, right? And then this is very simple orthographic projection. Our next step is that now when you do this kind of a viewing projection, also this orthographic projection, it still does not fit into the -1 into 1. So actually now the next step is that we convert the point into this normalized device coordinate. So everything should be between the -1 and 1. So then now we define this. We need to talk about the view volume. So in the case of the orthographic projection, we define view volume something like this. So actually your data basically before the projection, your data in the I space, and then the view volume is like this. We define the left and right. In other words, we can see the object only within this view volume, and then left and right, and bottom and top, and this is actually near and far. So in this case, when you are using this view volume, if the object is located very far away, so out of this far side, then we do not actually render them. So basically, we only render object defined in this view volume. So in this case, actually, we mapped this coordinate, this width and height and depth into this character space -1 to the 1. So basically, it's just nothing but we just scaling. So here, RL is the RL right and left, top and bottom, and far and F and N is the far and near. Basically, this actually scaling component. It's actually also projection here. Consider also the scaling scaling to map everything into the NDC space. It looks a little complicated, but actually you can actually if you put you can also you can check that whether it's correct or not. So for example, if you provide some point x point L, right, the left one, then what's the corresponding point in the any space? If the point the x value of x value of the x value actual point located in the left, it should be mapping to the -1, right? Let's see that whether it gives us the -1 or not. So you can see that if you put the L here, then if you do this operation, you have to multiply this one into the L, right? That's why the 2L minus R minus L. And then this Y and G cancels, and then you actually have this component here. If you do the operation, you will see that this gives us -1. I know it's a little bit, it may take some time for you to check it out, but I recommend you to pause the video here. Make sure that you can see, make sure that you can actually you can see that it's the left actually mapping to the -1. But here you can notice that actually for the orthographic projection, before we cancel out G component, right? But we didn't actually cancel out G component here. We will actually maintain G component is not a part of the orthographic projection, but we will use the G component later on for this visibility determination. For example, suppose that we have two triangles, right? So basically they are overlap in the space. Basically they are kind of overlap in your view space, right? Then we don't need to render this one, since actually this triangle blocked this behind the triangle, right? To decide which one actually is actually more close to you, we will utilize this G value. That's why we even under the orthographic projection, we maintain this G value, which will be used for the later on. Okay, so for performing orthographic projection, OpenGL provides this GL also. You might see the some of the API function GL also, right? When you are doing some programming assignment, basically GL also nothing but basically you specify you want to use this orthographic projection, and then each API is left, right, bottom, top, and near and far. You define the actual view volume, and these are actually some of the corresponding the API in this matrix form. Now let's talk about this perspective projection. You know that actually right now actually the perspective projection is very common, but this concept of perspective projection wasn't that intuitive a long time ago. So you know the history, actually somehow the perspective projection actually appearing reasonably recently, and then it's nothing but the object located close to you looks more bigger, right? And then object located far away from you looks smaller, right? So basically also this perspective projection, we want to realize this concept, and then you will see that actually homogeneous coordinate that we introduced before will allow you to do this perspective projection using this linear operator. It's nothing but the matrix of operations. So let's look at these are actually drawn by under this perspective projection. You can see that unlike this orthographic projection, some of we know that this is actually parallel line, but these parallel lines under the perspective projection actually intersect at a point, right? So we call it this actually the vanishing point, right? These are some of the signs of perspective projection. Now our question is that how can you do that? Actually, here I'm showing the illustration. Let me explain here. This E is the camera origin. This actually this view plane here. I want to actually and then this actually some point in the words this actually point in the I space, and then now I want to compute here. We also need to assume that what are actually the camera structure that we are using. Here we assume that it's pinhole camera. So actually here actually there's pinhole, and then some of actually this point can be seen through this pinhole, right? So they are mapping to the. So if you consider this camera, then there's pinhole, and you can see that this actually imaginary sensor frame. If you're using this analog camera, we usually put this film here, right? And then this object passing through the pinhole, and then they are actually arriving there actually. So but this actually what happened in the camera under the pinhole camera. But we don't use the film, right? But instead we put our this view plane here. Then the question is that I want to compute this coordinate here. Let's say this actually y direction, and then given this y coordinate of P, I want to compute this P dot in this view plane. By the way, here I mainly talk about this kind of pinhole camera. I actually talk about everything in a very simple setup, the pinhole camera, right? What if we are more complex actually the camera? You know actually, I guess you know that some of the recent cameras are much more complicated, right? So then if you're using the kind of the very complex camera model, we need to actually think about something else, right? So that's where these graphics become more graphics technique become more flexible. So initially we used a lot of these OpenGL and DirectX basically defined under this kind of very simple setup, camera and something like that, and the pinhole camera, right? But now actually the people wanted to have the more realistic effect, right? Like the effect seen through this complex the lens camera system. Then obviously we cannot use it, and then we need to think about some other techniques, right? So along that line, I will talk about actual ray tracing probably near this semester. But anyway, this concept actually very commonly adopted in the DirectX and OpenGL, and mainly to basically based on this simple setup, we can get a very fast performance, right? So that's actually we talk about this one. Okay, let's get back to our perspective projection. Our setup is that this camera origin, this actually the coordinate in P. I want to compute this location of this one into this view plane in the center of this pinhole. How can we do that? But you can see that you can very easily see that they're actually the same the shape of the triangle. The small one triangle or a triangle, right? Based on this ratio between them, we can actually derive the relationship, right? And then one simple setup is that here, so this view plane is located there, right? Then this is located there, the g value, right? This coordinate basically for this point, it has the y coordinate and g coordinate, right? So I just used the g here, and then basically when you have the g coordinate, it actually has a y. So my question is that what if I have this d? Basically the view plane located there, and this actually located a little away from this camera origin, right? This is here I define the d. This is nothing but a near plane. This is actually near. This d is nothing but a concept of near that I talked about in this view volume. Let me here. Actually. This is near and far. Near actually located there. Here, and then I use the d, and then I want to know what are the actually coordinate there. Y. Here, and the y frame. The y dot is nothing but this ys here. Here, and then you can see that this is nothing but dy divided by the g. Actually. Yeah, same formula, even though I used a little bit different notation. Yeah. So that's based on that concept, we end up with this one. The question is that how we can realize this division of the sum of the value within the matrix, right? We actually do a lot of the operation with the matrix vector operation, right? So now how can you do that? That's where we utilize actually the homogeneous coordinate. So we actually used this kind of the prospect projection. You can see that now it actually has a further the first row. Now we don't use the zero. We actually use the 0010, right? As a result, this the homogeneous coordinate after prospect projection has this. In this case, the W turn out to be the actually G, right? The turn out to be the W turn out to be the G, right? And then basically G is not other than the one, right? And then how can you do that? So even after this prospect projection, since this homogeneous coordinate is not the one, we actually we make it to have the one. To do that, we divided this the homogeneous coordinate with the G, right? And then we do the same operation to all the other x and y and g component after prospect projection. Then if you look at the here, and basically after this operation here gets the x, right? But if you divide the w, then x dot turn out to be the x divided by g, which we and the y dot also should have the y divided g, right? G component we under the perfect prospect projection we need to flatten, right? So g dot should be the 0, right? So we actually this is known as this homogeneous divide. If we do that, basically based on this concept, we can actually realize this the prospect projection. That's why we use this component, and then you should know aware of that. This the first coordinate, first law of this prospect projection has a little bit different form that we talked about to the common affine transformations. Okay, so also we can define the view volume, the prospect projection, right? So this actually common prospect projection, the view volume in the prospect projection. You can see that this is defined the near and far, bottom, top, and left and right. And then we also we wanted to, in the end, we want to use this NDC, the common coordinate, right? But usually the common process that convert from here to there is that we actually converted this view volume into the canonical prospect view volume, something like this. Everything mapped into the -1 and 1 in that one. And then also we can also transform this the prospective view prostom into the canonical view volume, this kind of the regular box shape. And then basically then at that point, basically whatever you use prospect projection or the orthographic projection, everything aligned with this view volume, right? And then we can very easily convert, we can very easily scaling this the canonical view volume into the NDC. As a result, this prospect projection considering this converting to the NDC looks a little bit complicated. But basically please believe me, this is correct one. And then if you actually basically the following the every step actually deriving that actual matrix is a little bit complicated. Also, it's not really important in this class. So just if you put before the prospect projection, if you have a coordinate like this x and g is left and near, then what kind of value you should have? The point is located in the left and near, right? Then if you look at the x, this point should be the mapping to there, right? Which is actually -1 for the x coordinate. If you actually put this number to there, apply this matrix, then you'll see that it will give us the -1. And then if you put initially if you had this g value turn out to be the far, you should have the 1 after perspective projection, right? If you put that number here, you will see that it will give us the 1. Actually, I did that also. That's why I made this equation. So I recommend you to try it out by yourself. That is that should be better for you to understand what's going on here. Okay, so we talked about actually the mathematical the process, right? But it's already very complicated to assume that everyone can understand this concept, right? That's why OpenGL actually hide all the low-level details and just provide this very simple API known as GL frostom. Also, the GL frostom defines the view volume left, right, and bottom, top, and near far. Then, if you call this one on the hood of this GL frostom, we define this kind of the matrix. We use it to realize this prospect projection. And some think that actually this GL frostom is already not intuitive. Also, there are some other corresponding, some other related function GLU perspective. It defines some other parameters. Like it also defines near and far, but also it use the different parameter. But visually, it defines this the field of view along this vertical side, this vertical field of view. Once you define this one, based on this aspect ratio between this aspect ratio, nothing but a ratio between this width and height. And then here you define this kind of based on that you can you also define the width and height, the rate. Basically you can compute this width and height. So some people actually prefer this kind of one. So there are actually this kind of API. But anyway, if you are using basically it's actually different parameter. But in the end, basically it boils. We are just using the same concept here. So also if you look at skeleton code of the PA2, we use actually GLU perspective. So actually field of view actually 45 degree. I don't remember aspect ratio. You can see that you can just assume the aspect ratio is 1, just the same width and height ratio, and one this actually near far, right? And then you can see that what kind of the view volume you can have, right? And then now let's look at some other component here. This is a reshape function. Here we define this viewport, right? And then we actually use the GL matrix mode, GL projection. Now we define projection, right? For a defined projection, we initialize it by calling load identity, and then we define this actual we define the aspect ratio, and then we pass down the information to the GLU perspective here. And then at that time we define this perspective projection. There got to be projection matrix, right? And then we also define the matrix mode, right? Matrix mode. So this model view. So depending on the application, actually you can actually you can actually transform the model in basically you transform the model from the model to the actually the world coordinate, right? And then once you define the coordinate in the world space, you actually go through this projection matrix. Okay, so that's it. So I wish that I talked about the different viewing projection, also this perspective projection, and then and I wish that you can understand by now. I wish that you can understand that this camera setup parameter, which are kind of intuitive. And then once you do that, you define actually this viewing projection, viewing transformation, and then also we talked about two different projection metrics. And by combining them, actually we can starting from the world coordinate, you do the actual viewing, and then you do the projection matrix. And then that way, actually, you now computed this coordinate in our image space. And then, if you're unclear on some of the part here, basically the chapter 4 of my book has more detailed descriptions. So if you're unclear, I recommend you to open up that book. Actually, you can go over you can get the more information over there. This regular homework: watch the 2 Sigma Asia video and submit their summary before the Monday class. Also, there is go over the next lecture material. That way, you can familiarize yourself for the coming materials. Yeah, and then that's it. And next time, I will talk about some other interactions. That's it. Thank you. Bye.